Hello everybody, this is Marco with Students Teach Orgo. I hope all is well. Today we will be doing two topics. So first we'll start with oxidation and reduction, and then a little bit later we're going to move on to the pinnacle rearrangement. So let's get right into it. Okay, so oxidation versus reduction. For organic chemistry, these really only involve one thing, and that is making or breaking bonds to oxygen. Oxidation is making bonds to oxygen, and reduction is breaking bonds to oxygen. How do we achieve this? With the help of reagents. And we're going to go through a couple of different oxidizing and reducing reagents to help you out in your practice problems. Now, before we do that, I should very quickly go over oxidation levels. Basically, an oxidation level just defines the number of bonds that a carbon has to oxygen. So there are four levels of oxidation levels. The first one is the alcohol oxidation level, which you can see up here on the top left. You'll notice that this middle carbon here is bound to one, or has one bond to oxygen, so that is OL1, oxidation level 1. The second level is the aldehyde or ketone level down here, and you'll see that that same middle carbon now has two bonds to an oxygen, right? Double bonded to this oxygen, so two bonds to oxygen. This is the second oxidation level. Third one is the carboxylic acid level. This carbon is now bound, or now has three bonds to oxygen. And then finally, we have the carbon dioxide level where it has four bonds to oxygen. Now, I should just quickly mention, these are not the same thing as oxidation states. So just keep that in mind. Oxidation levels are not analogous to oxidation states. Okay, now we'll get into the reducing agents. The big two are lithium aluminum hydride, or LiAlH4, and sodium borohydride, or NaBH4. For lithium aluminum hydride, there are a couple of things that it can do. So firstly, looking up here, it can oxidize aldehydes to primary alcohols, like you see here. Next, it can oxidize ketones to secondary alcohols. It can oxidize carboxylic acids to primary alcohols. And then finally, it can reduce esters to primary alcohols. And it will actually make two primary alcohols this way. It'll make one here and make a second one here. So it's kind of, in effect, it's kind of breaking this bond, if that makes sense. Now, it basically reduces anything on oxidation level 2 or oxidation level 3, right? So again, oxidation level 2, aldehydes and ketones, and oxidation level 3, carboxylic acids and esters, to alcohols, or oxidation level 1. So just keep that in mind. Now for the sodium borohydride, it's a weaker reducing agent, we say, than the lithium aluminum hydride, in that it will only reduce things on oxidation level 2. So it will take ketones and aldehydes and reduce them to secondary and primary alcohols respectively. Again, only reduces aldehydes and ketones, not carboxylic acids and esters. So it is a weaker reducing agent. Another thing that lithium aluminum hydride does is called reductive amination. This is a little bit different than with esters. So when you have an amide and try to reduce it with LiAlH4, you don't really get like a cleavage of this bond, like I said. What you get instead is this carbonyl oxygen kind of disappears. And what you're left with is this amine, this tertiary amine in this case. So just keep that in mind. Now, it might be a little bit difficult to memorize the different oxidating or the different reducing agents. What I found helpful when I took Orgo was having a table like this on, say, my note card for the exam, if you have that luxury, or just having it in your study guide for before the exam, and trying to memorize it this way. In most cases, you're only going to be dealing with this row here and with this row here. So makes it a bit easier, but if you are working with these other reagents, this is a very useful table. So yeah. All right, moving on to the oxidizing agents now. There is another big two here, PCC, or pyridinium chromochlorate, and the Jones reagent. So for PCC, it kind of does the opposite thing of NaBH4, where it takes primary alcohols and oxidizes them to aldehydes, right? So again, the reverse of sodium borohydride, and it takes secondary alcohols and oxidizes them to ketones. And it only does these two, really. Now the Jones reagent is a bit stronger in that it will take secondary ketones, or secondary alcohols, and oxidize them to ketones. And it will take primary alcohols and oxidize them to carboxylic acids, right? So in that sense, it's somewhat doing the reverse of lithium aluminum hydride, if you want to think about it in that way. So again, Jones reagent is a bit stronger than PCC, and they both will oxidize secondary alcohols to ketones, but they will do different things for primary alcohols. All right, let's get into some practice problems. So I encourage you to pause the video and unpause when you're ready. Okay, so let's consider first the left side of this molecule here. We have an amide on the left side, and we are reducing it with lithium aluminum hydride. So we'll recall when we have an amide and reduce it with lithium aluminum hydride, what we end up getting is an amine, right? Reductive amination, which is a bit different than what we're doing for stuff just with oxygen. So in effect, this O is going to just disappear, and we're going to be left with this tertiary amine structure there. On the right-hand side, we have a carboxylic acid, right? And again, recalling what lithium aluminum hydride does to carboxylic acids, it reduces them to primary alcohols, right? So what we're going to end up getting is just this carbon with a single alcohol group on it. So this is our product. Okay, practice problem 2. All right, so let's consider what the transformation is between our precursor molecule, our reactant, and then our product. The first thing I notice is this group here, this carbonyl group, is reduced from a ketone to a secondary alcohol. So that should tell you I'm using either LiAlH4 or NABH4. And then the second transformation is with this alcohol group out here, right? I see that this alcohol group is oxidized to a carboxylic acid. And right away that tells you that you need to be using the Jones reagent, right? The H2CrO4 Jones reagent. So the question is, am I going to react this here with the Jones reagent first, or am I going to try to reduce it first? You should be using the Jones reagent first. And this is why. If I use the Jones reagent first, then what I end up doing is I oxidize this alcohol to the carboxylic acid, and I still have this ketone here, right? And then between the two options we had for reducing this this oxygen, this ketone group on the left-hand side, again, I can use either lithium aluminum hydride, which would reduce the carboxylic acid now that we have, which we don't want to happen, or we can use sodium borohydride, which again will leave the carboxylic acid alone, right? Again, sodium borohydride doesn't touch things on oxidation level 3. So what we do here first is Jones reagent to oxidize our primary alcohol to a carboxylic acid, and then we use sodium borohydride to reduce our ketone to a secondary alcohol. Okay, and practice problem 3. Okay, let's go ahead. Let's start with compound A with the arrow pointing to the left. So in our reactant molecule, we have a ketone and we have an ester in this ring. Now again, recalling what sodium borohydride doesn't touch esters, but will reduce ketones to secondary alcohols. So that's exactly what's going to happen. This stays the same, and this becomes an OH. Now for reactant, or for product B, we are now, instead of reacting with sodium borohydride, reacting with lithium aluminum hydride, right? Which reduces ketones the same way that sodium borohydride does, but it will also cleave this ester here, right? Remember I talked about it kind of makes two separate primary alcohols by sort of breaking this bond, it seems. that's exactly what's going to happen. So first, we treat with the LiAlH4, and this becomes, this bond gets cleaved, so to speak, and we get two primary alcohols, and then this becomes an alcohol as well. I'm going to just redraw this really quickly to make it look a bit prettier and see what's going on. Now, our second step is reacting with the Jones reagent, which this is just the Jones reagent. It's just another way of writing it that you might see. Now we have to consider what the Jones reagent does, right? Primary alcohols to carboxylic acids. We have two primary alcohols here on the outsides of the molecule, and then this secondary alcohol to a ketone. So our final product is that molecule right there.